In this section, our objective is to be able to use properties of arcs, chords, and tangents of circles. Let's examine first some properties of tangents. Tangent property number 1, intersecting tangent and radius are perpendicular. So you see in this picture, this right here, this line is a tangent because it is only touching here, that at the point of tangency, and here is a radius. When a tangent intersects with a radius, they will intersect at a right angle. They will be perpendicular. You'll notice in this animation that no matter where I put that point of tangency, I can drag it anywhere in the circle. If it intersects the radius, that tangent is always making a 90-degree angle with the radius. So again, tangent, radius, perpendicular. They're going to make 90 degrees. Let's look at some examples that apply this. First, determine if segment AB is tangent to circle C. So if this segment is tangent to this circle, then here's the radius. This must be a right angle. So that's the question mark. Is this 90 degrees? How do we figure that out? Well, what does this look like? If this is a right angle, this is going to be a right triangle. How do we determine if this triangle will have a right angle? Pythagorean theorem, c squared equals a squared plus b squared. Now it's only equal if it's a 90-degree angle, so that's our question right now. We don't know if it's equal. Which side will have to be the c? The biggest, or the side across from the potential right angle. So this is our c. So 5 squared maybe equals 3 squared plus 4 squared. This side is 25, over here is 9 plus 16, and 9 plus 16 does make 25. So they are equal. Now we could have noticed that this is a 3, 4, 5 triangle, and 3, 4, 5 makes a triple, which we know is for a right triangle. So is segment AB tangent? Yes. Segment AB is tangent because segment AB is perpendicular to segment BC, this being the tangent, this being the radius. How about the second one? Maybe you can try that on your own, pausing the video, come back and see how you did. So if this is going to be tangent, it should be perpendicular to the radius. That's our question. Is it perpendicular? How do we figure out if this is a right triangle? C squared equals, maybe, a squared plus b squared. Across from the right angle, or the side that's the biggest, that's our c. 10 squared maybe equals 3 squared plus 9 squared. 100 equals 9 plus 81. 100 equals 90. Wait a minute, doesn't equal 90. So no, AB is not tangent to this circle. Why? Because AB is not perpendicular to BC. Let's look at the third example. Given the tangent segment intersecting with the radius and the secant segment shown below, find the radius of the circle. Find the radius. So they told us it's a tangent. And remember, tangent is perpendicular to radius. So if this is a tangent, then it has to make a right angle with the radius. Has to. Well, this 6 right here is labeling just this section from here to here. Notice how the 6 is in the middle of that segment. It's not in the middle of the long segment, so this is also a radius r. If we know that this is a right triangle, to find a missing length of one of the sides, we use the Pythagorean theorem. C squared equals a squared plus b squared. Now this is going to be a little tricky because we're not missing just an entire side, we're missing a piece of a side. So let's see how we can do this. Across from the right angle is the hypotenuse. This whole side is the C, the hypotenuse. Part of it's 6, part of it's r. How do we put those together? Add them. 6 plus r. So in the C, we're going to put 6 plus r. All of that will be squared. Then we can fill in the other two sides adjacent to the right angle, r squared and 9 squared. How do we square this? We write it twice because that's what square means, multiply something to itself, and then we FOIL it. Let's not forget there's a right side of the equation, so I'm going to write the rest. What does that mean to FOIL? Well, basically distribute. 6 times 6 is 36. 6 times r is 6r. R gets distributed. R times 6 is 6r, and r times r is r squared. And then we'll write the rest of the equation. Now we can combine like terms. Here's an r squared, subtract it because it's added, and do it on both sides. Luckily, it goes to 0 on both sides. No more r squareds. We can combine these like terms to 12r. So I have 36 plus 12r equals 81. Here's the r. I want it by itself, so minus 36 from both sides. Left over with 12r equals 45. Divide by 12. R equals 3.75. Exactly. Let's look at another property of tangents. Property number 2. Intersecting tangent segments are congruent. Let's take a look at this picture. It will be given that segment RS and segment RT make right angles with the radii of circle C. See, here's a right angle, here's a right angle. Well, if they make right angles, that means this has to be tangent because it's perpendicular to the radius, and this has to be tangent. So these are two tangents. Notice they intersect outside the circle at point R. What else can we determine? Well, if S goes to C and T goes to C, those two little segments are both radii. So since radii of the same circle are all congruent, we can put little congruent slashes there. SC is congruent to TC because they are radii of the same circle. What else? Well, notice we have a triangle on the top and a triangle on the bottom, and both triangles share this segment RC. So we can say it's congruent to itself. RC is congruent to RC. Do you remember what property tells us that? It's a shared side, but we say the reflexive property tells us that a segment is congruent to itself. So notice what we have here. A triangle with two congruent sides and an angle, a right angle, congruent to a triangle, two sides, and the right angle. So these triangles are congruent. Triangle RSC is congruent to triangle RTC by the hypotenuse leg congruence theorem. Why do we care? Well, because then it tells us that any corresponding parts have to be congruent, such as this remaining side and this remaining side. So therefore, we can say RS is congruent to RT by corresponding parts of congruent triangles being congruent. Well, remember, we said these two are tangent, so these tangents have to be congruent. Just a little reason why that's true. Let's take a look at an example of how to use the fact that intersecting tangent segments are congruent. So first of all, we identify in the picture that we have a tangent segment and a tangent segment. So this side is congruent to this side. How do we show that? Make them equal. And then we solve. And there we go. tangent segments are congruent.